Thanks for the introduction, and thanks for the invitation. Today I'm going to tell you a little bit about what arithmetic fundamental lemma is, and the end goal will be proof of some special cases of the AFL. But let me begin with some global motivation. Coming from the arithmetic version of the Ganguis-Poiseuille conjecture. Okay, so the story begins with a celebrated classical result of Gros-Zagier, which says that if you start with an elliptic curve over the rational, and you choose some specific imaginary quadratic extension of Q, then Gros-Zagier put a remarkable formula relating the first derivative of the elliptic curve based to this imaginary quadratic field at the central point. The arithmetic normalization center is at 1, is related to some particular algebraic construction called Hegener points. Which is a certain algebraic point of this elliptic curve over the imaginary quadratic extension. Okay, and there is a natural height pairing on the group of rational points known as the Néron-Tate height pairing. Okay, so this Gros-Zagier formula builds a link between deep analytic information about the L function of the elliptic curve with arithmetic geometric meaning information, namely rational points on this elliptic curve. Okay, so this formula has been the basis of remarkable recent progresses on the Bertrand and Swinnerton-Dyer conjecture for elliptic curves of rank 0 or 1. Okay, so the arithmetic Ganguis-Poiseuille conjecture seeks a generalization of Gros-Zagier formula to not just elliptic curve, but more higher dimensional Shimura variety. Okay, so particularly consider the following two pairs of groups. The orthogonal group of signature 2 and 2 into the bigger orthogonal group of signature 2 and 1, or so you can consider unitary group of signature n1 n minus 2 and a unitary group of signature n minus 1 n minus 1. Okay, what's good about these embeddings? Well, if you look at the corresponding map on the Shimura variety associated to these pair of groups, okay, and you compute the dimension of the Shimura variety, that's exactly encoded by these numbers. Okay, and what you see is that, well, I'm actually constructing very interesting divisors in this ambient Shimura variety. The sub-Shimura variety is of codimension 1. Okay, so for arithmetic study, for example, you want to compute certain height pairing, you want to make sure your subvariety or cycle, algebraic cycle in general, lies in arithmetic middle dimension. Okay, now you can play the game by starting with a divisor by looking at the diagonal embedding from the smaller Shimura variety to the product Shimura variety. Okay, now you count dimension. The smaller one is still n minus 2, and the bigger one is, of course, the sum of these two. Okay, and So they have geometric dimension n-2 and 2n-3. So arithmetically, if you consider integral model, this is n-1, this is 2n-2, and this is exactly arithmetic middle dimension. Okay? So this construction gives me giving me an interesting cycle. By abuse notation, I still call it delta, meaning diagonal under the diagonal map of this smaller Schimmer variety. So it's arithmetic middle dimension. Okay, so now I can state a rough version of the arithmetic Gangres-Pessard conjecture, aiming to generalize the Grozagi formula. Okay, so if I start with a tempered Caspidal automorphic representation of the product group appearing in the middle dimension cohomology of the Schimmer variety associated to the product group. Okay, then I should have equality between some analytic information, in this case, certain Rankin-Selberg type L function at the central point. Okay, and certain arithmetic information, okay, encoding to this cycle I constructed, and it's now called the GGP cycle. Okay, so you can take a pi isotypic component of this GGP cycle, okay, and do the higher dimensional analog of the Néron-Tate pairing, known as the Beilinson-Bloch height pairing. Okay, so that's the vast generalization of the original Grozagi formula. So let me give you some examples. Okay, so you can consider some lower dimensional example. Let's say n equals to 2. If you look at the orthogonal family, so H times G is SO2 cross SO3. And in this case, the GGP cycle is nothing but the zero-dimensional variety on a one-dimensional variety. So that's a Huygens point considered by Gross and Zagi curve. Okay? So this, in this case, that's just the original Grozagi formula. Reduced the arithmetic Gangres-Pessard conjecture reduced to the Grozagi formula, and in most general form due to Yuan Zhang Zhang. Okay, so the next case, n equals to 3. Okay, so now you are looking at a cycle of one dimension, a curve, lying in a product of a curve and a surface. Okay, a special case is the Gross-Schoen cycle considered by Schoen on a triple product of modular curves. Okay, and in this case, many instances of the arithmetic Gangres-Pessard conjecture has been also proved by Yuan Zhang Zhang. Okay? So you can continue to list what kind of examples of this higher dimensional Shimura variety, and it turns out to be very interesting in itself. For example, you can take SO5, or better G-spin 5, that's essentially GSP4, the corresponding Shimura variety is a classical Ziegel moduli variety of abelian surfaces. Okay? So you can look at SO6, that's a moduli space of abelian fourfold with complex multiplication. And look at SO8, that's moduli space of abelian eightfold with quaternion multiplication. All the way up, you can go all the way up to SO21. That's a famous moduli space of polarized K3 surfaces. Okay? So understanding cycles on these moduli spaces are themselves very interesting. Okay, but unfortunately, beside these two lower dimensional cases, the AGGP conjecture is still widely open. Okay, so remark, GGP still widely open. For n at least 4. Okay? So the goal of the arithmetic fundamental lemma arises from attacking the general case of AGGP conjecture using relative trace formula. In the unitary case, unitary GGP by the relative trace formula approach. Okay, so what is this relative trace formula about? Well, let me firstly remind you the usual version of the GGP conjecture, the unitary GGP conjecture. Okay, the non-arithmetic version. Okay, so this is relating the central L value of a similar type, but the value of the L function with certain automorphic period. Okay, so Jagged-Rallis proposed compare two relative trace formula in order to attack the unitary GGP. Okay, so one on unitary group. Where you take the two subgroups to be the diagonally embedded smaller unitary group. Okay, and compare with another relative trace formula for the other triple, but on general linear group. Okay, so E over F is a quadratic extension defining my unitary group. Okay, on the left you quotient out by the diagonally embedded GL n minus 1. On the right hand side, mod out by the general linear group over the base field. Okay, so this familiar period integral will give us the central L value, and left hand side, this Flicker-Rallis period will detect the base change of automorphic forms from unitary group to general linear. Okay, so if you have a comparison of these two relative trace formula and do a spectral decomposition, that will give rise to the desired consequence spectrally. The period integral related to the central L value, the base change of this automorphic representation. No. Tempered, yeah, tempered is no. Okay, any questions so far? Okay, yeah. Twist. What? I don't understand the question. Sorry. Okay, so in order to compare this, I need to, of course, compare the geometric side of these two relative trace formula. Okay, so you can identify both orbital in space as, in this case, as just some conjugation action on unitary group on the left-hand side, and also the conjugation action on certain symmetric space where okay, so these are matrices satisfying GG bar equals to 1, where bar is a Galois conjugation for E over F. Okay, so in fact, there is a matching of orbits. Okay, so let me describe in the case that will be interest to us, the case of a non-ramified quadratic extension over local fields. So let's assume E over F now is in local situation. Mention p-adic fields. Okay, so there are two isomorphism class of Hermitian space over a local field. So the left-hand side, we are exactly getting a disjoint union of these two orbits from these two Hermitian space. Okay, which I call one of the Hermitian space Vn, regular semi-simple orbits, disjoint union with another Hermitian space, which I call Cn. So this one is a split one, split Hermitian space of dimension n, and this one is the non-split one. Regular semi-simple orbits is in bijection. The regular semi-simple orbits on the right-hand side. Okay? So there's a natural matching process between the orbits of these two sides. Okay, so naturally when you're comparing these two geometric sides, there's a key local ingredients, namely a fundamental lemma asserting an identity between orbital integrals on both sides for the unit test function. So the Jaquet-Rallis fundamental lemma. So F, I take some orbit on the left-hand side corresponding to the split one. And matches some regular semi-simple orbits on the right-hand side. And the orbital integral for G for the unit test function on the unitary group. Okay, should be equal to, or up to some simple transfer factor, turns out to be a sign in this case. Okay, the orbital integral on the symmetric space. Okay, so I think for audience here, this should be expected. Okay, but it sort of asserts a remarkable identity between two types of orbital integrals on two different spaces. Okay? So this fundamental lemma of Jaquet-Rallis has been proved by Zhuo Yun and Julia Gordon. Okay, by first using the geometric method after Go, and then transfer the results to field of a characteristic 0 for sufficiently large P. Okay, and recently, just last week, there's a new proof, a purely local proof due to Raphael, sort of avoids the use of geometry, and in fact, this proof is remarkably short. Okay, so as Wickett was joking that now this short proof justifies the name of a lemma. Okay, it's only 7 pages. Okay, in any case, we have this wonderful result that allows you to compare the Jaquet-Rallis relative trace formula approach, and that's sort of the basis of Wei-Zhang's proof of many cases of the unitary GGP conjecture. Also, yeah, builds on Wei-Zhang's smooth transfer and compatibility with partial Fourier transform. Okay, so now we want to sort of modify this matching a little bit to encode the arithmetic information. So for unitary AGGP, Okay, I need to two modification. Okay, so one modification is I want to get not just the central L value, but rather the central derivative of the L function. Okay, so in order to do that, it's very simple. So instead of considering this orbital integral on the symmetric space, I'm going to instead considering a derivative of orbital integral by first inserting an s variable and take the derivative with respect to x. Okay, so I'm going to replace this orbital integral on the symmetric group side, symmetric space side, by derivative orbital integral, which is defined as follows. Okay, so I'm going to take the orbital integral of this unit test function okay, so that's the original form of the orbital integral. Okay, but now inserting an s variable, taking the absolute value of the determinant of h to the s power. Okay, so now I have not done. So this is the s variable, so I want to take the derivative and evaluate at the point s equal to 0. The smaller GLM minus 1. Okay, so that's the modification you need on this side. So I also need to make some modification on the left-hand side. Okay, so on the other side, on the unitary group side, I'm going to do a modification so that originally I get the period integral. Instead, I'm getting a height pairing. Okay, so that's where the story becomes dramatically different, because I'm going to get some arithmetic geometric information. So I'm going to replace the orbital integral of g in the unitary group by something I call int g. Okay, so this int doesn't represent integral, but means intersection. So it's a arithmetic intersection number. Okay, related to this group element g. Okay. On what? On a local analog of the Shimura variety, on a local Shimura variety. Okay, well, that's known as the Rapoport-Zink space. Okay, so this is something I need to define for you. Okay, but the purpose of this intersection number is to eventually globally will give you this height pairing of algebraic cycles. Okay, so now I can state the arithmetic version of the Generalizing fundamental lemma. Okay, so remember we only use half of the orbits on the unitary side, so I'm going to use the other half. Okay, so that's the content of the arithmetic fundamental lemma. Okay, it says that if I have G as in the non-split Hermitian space, okay, and matches some elements in the symmetric space. Okay, so as I said, I'm going to replace the left-hand side by some local intersection number, some explicit transfer factor, and the orbital integral derivative at s equals to 0. Okay, so I hope this makes sense. That's this sort of statement of the AFL conjecture. So first remark, what is some evidence of this conjecture? Well, I think I'm a little bit lying, because when you take the derivative of this orbital integral, it's not quite an integer, so you need to also take the ratio of log q, where q is the size of the residue field. Okay, that's when you take a derivative of exponential function, you need to get some natural factors. Okay, so this is again a remarkable identity between two numbers, and two numbers of very different nature. That's a derivative orbital integral, that's more familiar, but left-hand side lies in a quite different world, the world of arithmetic geometry. Okay? But anyway, that's two integers, and the conjecture is that these two integers always match up with each other. Okay? So Wei Zhang, after he formulated this conjecture, did very delicate calculation, proved AFL. In the low-dimensional cases, that is sort of more attractable by just brutally computing both sides. Okay, and in each case, they match up perfectly. Okay, but somehow for the global purpose, it's not very desirable, because we already know that many cases of the AGGP has already been proven. Okay, so the question is, well, can you verify this identity for higher dimensional cases? Okay, so now let me quickly state the main result. Okay, so that's the main theorem of this talk. Xu He, self, and Yang Zhu. Okay, so the conjecture AFL holds. Okay, so this is for any n, not just lower n. AFL conjecture holds when G, right? So this is a group element in this unitary group. Okay, is minuscule. Again, I owe you the explanation of this term. Okay, so I hope to define this condition minuscule. Okay, and hopefully I will explain why this condition is necessary to prove any results using our method. Okay, and why it helps us to prove the AFL in this case. Okay? Any question about the statements? That's a hope. It's not clear at the moment. Okay, at least it gives you a sort of a basis to work on for any n, this sort of identity. But let me first say, this is some of this theorem is not new. So remark, so Rapoport, so in the case where the base field is just a QP, and when you have a restriction on the P, and P is sufficiently large compared to M, the theorem is already known. First proved by Rapoport-Zink, in 2013. Right, they also had this condition that for global purse you really would like to remove. Okay? You want a fundamental lemma and AFL to be true at all unramified places. Okay? But let me just remark, even in these cases, our proof is completely different from theirs. Okay? So our proof is different. Okay, in fact, the way they prove, okay, like ours, the proof, of course, is difficult part is to compute the arithmetic intersection number and use powerful tools from deformation theory of p-divisible groups to literally compute the left-hand side of this arithmetic intersection number. It's an explicit computation used up about 20 pages just computing one thing using linear algebra. Okay, so in some sense, our proof is slightly more conceptual in the sense that eventually the explicit computation, essentially we can avoid all the explicit computation except the last step. Okay, so let me try to explain how this works. Okay, again, I owe you the definition of minuscule and also rigorous definition of the intersection. Okay, so let me first try to introduce the definition of this inter G. Okay, first let me introduce a notation for the Rapoport-Zink space. Let n Zink space associated to this non-split unitary group. Okay, as I said, this is a local analog of the Shimura variety. I think rather than, instead of describing the definition, the technical definition of this space, let me just describe some properties of this space that are actually useful when you work with them. So first of all, what is this object? It is a formal scheme. Okay, over an integral base given by the spuf of the ring of integer of E Grever, where Grever is the completion of the maximum unramified extension of this quadratic extension E. Okay, so what is this space supposed to do? Well, this is parametrizing deformations of unitary p-divisible group. These are p-divisible groups with extra structure S coming from the unit group action. Divisible groups. Okay, so deformation of what? Of a fixed unitary p-divisible group x0 over k, where k is a residue field. Q bar. Okay, so this p-divisible group has dimension n and height 2n, and signature condition u1 and minus 1 is also played in a role in this definition. Signature (1) and minus 1. Okay, anyway, this is some concrete deformation space of some concrete p-divisible group over the residue field. Okay. And third, well, why this is called a local Shimura variety? Because it has a relationship with global Shimura variety. So it provides a p-adic uniformization on the Shimura variety associated to this unitary group, supersingular locus over K. Okay, so by this uniformization, it will eventually relate to the global information about the Schumann variety. And finally, let me give you some intuition about this space. For example, what's its dimension? Well, its dimension, let me call it S is birth of the relative dimension of this space is the same as the dimension of the unitary Schumann variety, -1. Okay, but this is a formal scheme, so it's highly non-reduced. So you can ask, what's the reduced part? Okay, so the reduced locus of this Rapoport-Zink space is dimension has a -1/2. Okay, so it's essentially half dimension. Okay, so the difference between these two numbers shows that the Rapoport-Zink space is highly non-reduced. In a lot of formal direction you can go around. Okay, so the structure of this reduced, underlying reduced subscheme of this formal scheme is studied by Vollard and Wedholm. In a paper in 2011. Okay, so let me give you an example. Okay, so let's consider the simplest case n equals to 3. So I have this Rapoport-Zink space live over this one-dimensional base S. Okay, so this S has a special point given by a spec over K of the residue field. Also have some generic fiber. Okay, so the dimension should be 2. So the generic fiber is some rigid analytic surface. Okay. Also, the special fiber is some formal scheme of dimension 2 over K. Okay, so if you plug it into the formula, I know the reduced structure should have exactly one dimension. So I get some reduced curves inside this picture. And in fact, you can follow the recipe of Vollard and Wedholm very explicitly and describe what this special fiber, the reduced fiber, looks like. Okay, so in general, it looks like some different irreducible component of the curves and intersecting in a very interesting and complicated way. Okay, but just in this case, each component is isomorphic to, it's a curve. What is this interesting curve? Okay, that's exactly a curve defined by a Fermat equation of degree q plus 1 inside P2. Okay, and the geometry of these components turns out to be important for the purpose of a calculation. Okay, so that's the description of the ambient Rapoport-Zink space. Now let me define what the intersection number should be. Assume. Okay, now consider a relative situation. Suppose my ambient Hermitian space can be decomposed as another non-spatial Hermitian space of one dimension lower, orthogonal direct sum with one vector where the vector has norm 1. Okay, so now I can look at similar picture analogous to the global situation. I have the unitary group of the smaller Hermitian space to the bigger one. Okay, correspondingly, they will induce an embedding of the Rapoport-Zink space, okay, of one dimension lower to the ambient Rapoport-Zink space. Okay, again, I told you the dimension count, so this should be sort of as a divisor. So if I want to do intersection theory, I better, again, play the trick of embedding the small one to the product. Okay, so I get a local GGP cycle, which is the image of delta, a smaller Rapoport-Zink space, now inside of the product space. Okay, so that's the local analog of the cycle I'm going to consider. Okay, so by the construction of this Rapoport-Zink space as a deformation space, I know this unitary group would act on this Rapoport-Zink space. Okay, so now I can consider the local GGP cycle together with the translate of the GGP cycle by this group element and do the arithmetic intersection. Okay, so that's going to be a number defined to be, so the thing you usually see in intersection theory is by considering the Euler characteristic over the ambient space. Okay, all the two structure sheaves defining these two cycles. Okay, but in general, the intersection of these two cycles may not be proper. They may have non-transverse intersection. So in order to make sure this is well behaved, what you actually need to do is taking the tensor product in the derived category and compute the Euler characteristic in the derived category. Okay, so to deal with improper intersection. Okay, but because, as I said, the Rapoport-Zink space is highly non-reduced, and in general, the position, relative position of these two cycles are very complicated. So in general, this is a highly derived thing, and it's very impossible to compute. Okay, so now this is the key point of introducing this minuscule condition that gives you some hope to compute this arithmetic intersection number. Okay, so now definition of minuscule. Okay, so first of all, let me remind you, say G is regular semi-simple. Okay, so one of the equivalent formulation in this case is to consider the following lattice generated by G, and the additional vector I added it to the smaller Hermitian space by looking at the iterated action of G. Okay, so that's the subspace of Hermitian space. Okay, I say it's regular semi-simple if what you generated is actually a linear independent. It's a full rank OE lattice. Okay, so that's the definition. Now further say, G is minuscule. Okay, if the usual minuscule condition on this lattice is satisfied, meaning that the lattice is squeezed between its two dual lattice, LG check, and the uniformizer times the dual lattice. Okay, so in particular, the dual lattice quotient out by the lattice itself is actually a vector space over the residue field. Okay, so that's the minuscule condition. How does that help us? Well, it helps us in two ways. G minuscule would imply two things. First of all, the analytic side, the orbital integral derivative, is very easy to evaluate. And more important for us is that now this arithmetic intersection number has a non-derived interpretation. It's the length and the K-scheme of the naive intersection. The GGB cycle together with its translate. And in this case, you can actually prove this is an Artesian scheme. Okay, so what we actually measure in this arithmetic intersection is what naively should be true, namely counting how many intersection points there are and add the multiplicity, intersection multiplicity at each point. That's exactly encoded by this K length of this Artesian scheme. Okay, so it reduced to theorem A. Reduced to the following explicit formula. Now I said the analytic side already has the explicit formula. And it remains to compute the arithmetic intersection number. Okay, so reduced to explicit formula. And G is minuscule. Okay, so my next goal is to tell you what this explicit formula looks like. It turns out to be exactly encoded by some elementary invariant, namely the characteristic polynomial of this element G acting on this quotient space. Definition. Okay, so now this is a Hermitian space. With residue field E, namely FQ squared. Okay, so G stabilize both G, LG and LG check. So induces an action. Okay. Now, as a group element over a finite group of Lie type. Okay, so let F to be a characteristic polynomial of G bar. Okay, so that's a polynomial with coefficient in FQ squared. Okay, so in order to state the formula, so let me describe some invariants of this characteristic polynomial. Okay, definition. For any polynomial Q write its factorization into roots over the algebraic closure. Okay, then we define another polynomial, star. It's reciprocal. Okay, by just reversing all these roots after applying the Galois action. Okay, so why do I define it in this way? Because if you take any element in the unitary group, this characteristic polynomial will satisfy this property. Okay, and F star is equal to F. Okay, so final piece of notation. For any irreducible factor Q dividing F, write MQ to be its multiplicity. Okay, theorem. Okay, so that's the real theorem that lies behind the main theorem on AFL. Okay, assume the intersection number is not zero, then there exists a unique irreducible factor Q0 of F, such that two conditions are satisfied. First of all, this factor is self-reciprocal. Q0 star is equal to Q0. And second, its multiplicity must be odd. Okay, so that's a sufficient condition. So if your intersection number is non-zero, it intersects non-trivially, then you can find a unique self-reciprocal factor such as the multiplicity is odd. And in this case, the intersection number can be explicitly written as the following formula. Okay, so I already know this is an odd number, so I can add it by 1 and divide it by 2. That's still an integer. Degree of Q0. Then multiply all the pairs Q, Q star, such that Q is not Q star, not self-reciprocal. Okay, look at all these non-self-reciprocal factors and multiply 1 plus their multiplicity. Okay, so that's very explicit. I hope you don't use too many symbols, but it's a very explicit formula for the intersection number. Okay, and you do the calculation on the analytic side, and it turns out to be the same number, miraculously. Okay, so now finally, let me briefly describe two ingredients of proving this theorem B. Okay, and let's explain, well, if you want to compute this arithmetic intersection number, in general, it's highly non-reduced picture. How can you compute it sort of explicitly? The first ingredient, the theorem I proved with Yinhang Zhu earlier, it says that if you impose this minuscule condition, then when you compute this naive intersection of the local GGP cycle, it can be actually reduced to a purely algebraic geometry problem. So this is a smooth projective variety over the residue field K. Okay, by computing an automorphism induced by this group element G on a smooth projective variety over this over the residue field. Okay, computing this fixed point. And immediate corollary is that it gives you a conceptual interpretation of this arithmetic intersection number by applying the left-shift trace formula. By computing the trace of G bar acting on this cohomology of adic cohomology of this smooth projective variety. And in fact, what is this more known about this smooth projective variety? Well, this is an example of a closed fine Deligne-Lusztig variety associated to some partial flag variety of the finite unitary group. Okay, so that's the first ingredient. So let me not discuss the proof of the theorem, but it uses Grothendieck method theory to do some elementary deformation calculation, then combine with the results of Vollard-Wedholm I described earlier about the geometry of the reduced structure of the Rapoport-Zink space. Okay, so this corollary immediately raises a question, well, can you compute the trace of group element on the cohomology of this closed fine Deligne-Lusztig variety? It is not obvious because this is not a Deligne-Lusztig variety considered by Deligne and Lusztig. It's not a classical Deligne-Lusztig variety. But it turns out there's some natural, very natural inductive structure on this fine Deligne-Lusztig variety. There exists an explicit character formula for closed fine Deligne-Lusztig variety. Okay, including all those appearing basic loci of Shimura varieties of Coxeter type. Now V appearing okay, so this is a rather general formula, gives you a character formula for a wide class of fine Deligne-Lusztig variety. In particular, that helps you to do this explicit computation of the trace. Okay, and theorem B would follow by combining these two ingredients, 1 and 2. Okay, I think I have 1 more minute. Let me just say one word how this theorem, the character formula, is proved. Idea. What we observe is that this closed fine Deligne-Lusztig variety has a nice stratification, locally closed stratification, okay, into a locally closed fine Deligne-Lusztig variety, and each xi can also be related via parabolic induction. Okay, so for some parabolic subgroup of the finite unitary group, okay, with some classical Deligne-Lusztig variety. Okay, so let me end with this specific example I mentioned earlier. Okay, example, let me take X to be a Fermat curve. Okay, I wrote down earlier. It turns out in this case, it's already an interesting stratification. Okay, so what is this stratification? Well, you can look at the rational points of this Fermat curve. Okay, it turns out to be exactly PQ q cubed plus 1 points. Okay, and this is the Deligne-Lusztig variety associated to the unitary group. And now you can interpret this discrete set of q cubed plus 1 points as an induction from a zero-dimensional Deligne-Lusztig variety, just induction of points. Okay, so this is points. Okay, but now you can finally apply the classical character formula of Deligne-Lusztig and compute the trace of any group element on the cohomology of this fine Deligne-Lusztig. Okay, so that's all I want to say. Thank you for your attention. Right. Yes. Say it again. Unramified, yes. That's a good question. So the question of the relative trace formula at a ramified place also makes sense. And this is the content of arithmetic transfer conjecture. Okay, so the relative Rapoport-Zink space is replaced by another Rapoport-Zink space of exotic smooth reduction. Okay, but in this case, the arithmetic fundamental lemma is not that simple, but it's encoded in the conjecture of arithmetic transfer. So now in this case, the situation is ramified. Yeah, I believe so. So in fact, the way Zhuo-Yun proof, the geometric proof is actually building on it's a simpler case of the identity can be directly verified by just lattice counting. That's one of the ingredients. In the minuscules, you can get the formula because it's counting lattices satisfying certain property, and the minuscule condition allows you to reduce lattice counting over a finite field. But that can be done very easily. Well, in the non-minuscule, so if you take G bar to be non-minuscule, take G to be non-minuscule, then this theorem is already not true. So I cannot interpret it, the intersection number, in terms of the Deligne-Lusztig, right? So somehow the minuscule condition is to produce this variety. When you see this finite group, then there's no minuscule condition at all. It's completely general.